Let's investigate the effect of media on the angle of refraction for situations where light is traveling from an optically less dense medium to an optically denser medium. So what we're going to do in this investigation is we're going to keep the incident medium constant at A, and we're going to change the optical density of the refracted medium. And we're going to see how does that affect the degree of refraction. In all cases, because the light is traveling from an optically less dense medium to an optically denser medium, the light is going to be bent towards the normal. So what is our focus question? How does refracting medium affect the extent of refraction? What must we control between our treatments so that this is a fair test? The medium that the light moves from, which we could call the incident medium, the angle of incidence, and the wavelength of light. Now we could choose anything for these as long as we are consistent between the treatments. I have chosen for this particular investigation to go with air as the incident medium in all cases. I'm going to use 30 degrees as the angle of incidence in all cases, and I'm going to use red light of wavelength 650 nanometers. So now we need a table into which we can put our data. Complete these gaps for the table that we're going to use. Remember that the independent variable is refracting medium and the dependent variable is extent of refraction. So here we have tables showing the relationship between refracting medium and extent of refraction for light moving from air. So the incident medium is air, and air's refractive index is 1. So N1 is 1, and our angle of incidence is 30 degrees. Theta 1 is 30 degrees. Now I expect what you probably wrote here for the first column's heading is refracting medium. But now what you have to understand is that the headings of the table do not necessarily have to be the independent and dependent variables. They are rather the indicators of the independent and dependent variables. In simple experiments, those two are the same thing. The indicator and the variable are the same thing. But for more advanced investigations like this one, they are not exactly the same thing. The independent variable here is refracting medium. But we are going to use an indicator to tell us about refracting medium. Because if we were to just write the medium's name, glass, air, whatever, it would be a qualitative measurement. And we want a quantitative measurement. So we are going to use the indicator that tells us about the refracting medium, the quantitative indicator, which is the refractive index of the refracting medium, in other words N2. So you can see that they are related. Refracting medium and the refractive index of the refracting medium, they are related to one another. A similar thing applies to the dependent variable. Our dependent variable is extent of refraction. But again, extent of refraction is a qualitative variable. You give a description, high or low, and we want a quantitative indicator of that. And the indicator we use is angle of refraction. That's what we're going to measure, and it's a nice numerical, a quantitative indicator. We will just have to be careful, of course, when we interpret what angle of refraction tells us about extent of refraction, as we've discussed in previous movies, and we'll refer to it again. So now we're ready to collect our data. First of all, though, we need to decide what refractive indices are we going to use, and we can decide whatever we like, as long as we get a nice range. And I've decided on 1, 1,1, 1,2, 1,3, 1,5, and 1,6. So now we need to collect our data using a simulation. So I'm going to use the bending light simulation. I open more tools. Now remember, in all cases, we're going to control the incident medium as air. And another thing we're going to control is the angle of incidence, and we've decided that to be 30 degrees. We put on our light, we show our angles, and we get 30 degrees as our angle of incidence. We don't need to put a protractor in, but let's do it anyway, and we make sure that we position it correctly like that. So remember, the thing that we are varying in this investigation is the material of the medium into which the light goes. the refractive medium. So we're going to change the index of refraction of this medium. And our first measurement is with this medium having a refractive index of 1. So notice that is actually then not refraction that's happening, because the top medium is air and the bottom medium is also air. So the incident and refracted media are both the same medium. So there is no boundary between media really. And so unsurprisingly, the angle of incidence and angle of refraction are the same as one another, meaning there is no refraction, there's no bending happening. The light is just going straight through. Our next measurement is with the refractive index of this medium being 1,1, and we read an angle of refraction of 27,1 degrees. Our next treatment has medium 2 having an index of refraction of 1,2, N2 equals 1,2, and we find an angle of refraction of 24,6 degrees. Next treatment, index of refraction is 1,3, which is slightly optically less dense than water. Angle of refraction 22,6 degrees. Next treatment, N2 1,5, which is glass. Angle of refraction 19,5 degrees. And last treatment, we take the slider here all the way to the end and we get an index of refraction N2 of 1,6. Angle of refraction 18,2 degrees. So here we have our data entered into the table, and now we need to answer our question. Our question is, how does refracting medium affect extent of refraction? We've been using the indicator of extent of refraction, angle of refraction, but we now need to convert in our minds how is that related to our actual dependent variable, extent of refraction. So I've added another column here, and what you should do is identify which has got the highest extent of refraction, which has got the lowest extent of refraction, and write that into that column. Now remember that for light traveling from an optically less dense to an optically denser medium, the light is refracted towards the normal, and as a result, a small angle of refraction actually means more extent of refraction. As you can see here, on the left, we have the light being bent. It's not just going straight through. Whereas on the right, the light is not being bent at all, it's just going straight through. On the right, the angle of incidence and angle of refraction are the same as one another. It happens to be 30 degrees here. Whereas on the left, the angle of refraction is smaller than the angle of incidence because there has been bending occurring. And the angle of refraction here is 18,2 degrees. Obviously, 18,2 degrees is a smaller number than 30 degrees. But in the case of the 18,2, there has been bending. In the case of the 30, there hasn't been, because for light being refracted towards the normal, the small number of angle of refraction actually corresponds to a greater extent of refraction. So when we interpret this data, we must remember that. So in the case of the angle of refraction being 30 degrees, the same as the angle of incidence, there's zero refraction happening. 27,1 shows a low degree of refraction, and the highest extent of refraction that we're getting is for an angle of refraction of 18,2 degrees. The smallest number that we have for angle of refraction actually corresponds in this case to the highest extent of refraction. So when we answer the question, how does refracting medium affect extent of refraction, we must bear that in mind. And what is the answer to this question? We can give it in this format. As the independent variable is increased, what happens to the dependent variable? Does it increase or does it decrease? And I hope what you've said is, as the refractive index of the refracting medium is increased, the extent of refraction increases. So we can see here 1,6 was our highest refractive index. That was the most difficult material that the light was going into, and that caused the greatest extent of refraction. We can also word this as the optical density of the refracting medium is increased, the extent of refraction increases. So 1,6 was our highest N2, meaning it's the slowest that light can go through. Remember, N2 tells you how much slower the light travels than through a vacuum. So for this last medium, the light is traveling 1,6 times slower than through a vacuum, which is the slowest of those that we tested. And for that one, the medium with the greatest optical density, the most difficult medium, we got the greatest refraction, most bending happening.